Today we are going to discuss about the chapter electromagnetic induction. It is very important for examination point of view. So in this chapter, the first topic is Faraday's experiment. This Faraday's experiment is the converse of Oersted's experiment. In Oersted's experiment, we have discussed that when current passing through a coil or a conductor, it acts like a magnet. That means it produces magnetic field. So according to Oersted's experiment, when there is a change in the current, magnetic field is produced. Now this Faraday's experiment is converse of that Oersted experiment. Converse means reverse of that experiment. So in that Oersted's experiment, when there is a change in the current, magnetic field is produced. But here, when there is a change in the magnetic field, there will be a change in the magnetic flux. When there is a change in the magnetic flux, an induced EMF is developed in the circuit. This induced EMF is called induced electromotive force, and this phenomena is called as electromagnetic induction. That is what this chapter. So in this chapter, we are discussing about Faraday's experiment. That means this Faraday performed many experiments, and using these experiments, he explained two laws. Those are Faraday's laws. Those Faraday's laws are very important for 2 marks in IPA. So in this first experiment, you can say that there is a magnet, and this magnet is having north pole and south pole. And we know that when there is a magnet, around that magnetic field will be there up to certain extent. And we also know that magnetic field is represented by the magnetic field lines. You can see here, these are magnetic field lines. When this magnet is moving towards this coil, what he observed, that is the first experiment. So in this experiment, you can see this is a coil, and this coil is connected to a galvanometer. If you observe here, there is no battery. It is connected to a galvanometer. Now this coil is at rest position, and a magnet with its north pole facing towards the coil is brought towards the coil. So when this magnet is moving towards the coil, the number of magnetic field lines cutting across the area is changed. That indicates there is a change in the magnetic flux. So when these magnetic field lines, that means when this magnet is brought towards the coil, he observed there is a deflection in the galvanometer. That means this galvanometer pointer has shown some deflection. Then immediately he moved this magnet away from the coil. Then he observed the galvanometer started showing the deflection in the other direction. And his second experiment is this. Okay, this is a coil. This coil C1. This coil is connected to a galvanometer, and there is another coil that is connected to a battery. We know that when battery is connected, current passes through the coil. So current passes through this second coil, coil C2. And we also know that according to Oersted's experiment, when current that is passing through the coil, it acts like a magnet. So now this coil is acting like a magnet. When this coil is brought towards this coil C1, he observed that there is a deflection in the galvanometer. Then he started moving this coil C2 away from coil C1. Then he observed the galvanometer started showing the deflection in the opposite direction. That means in the experiment, he observed the same effect what he observed here. So from these two experiments, he concluded that when there is a change in the magnetic flux, when the magnet is moving towards this coil, there is an increase in the magnetic flux because the number of magnetic field lines cutting across the area increasing. So there is an increase in the magnetic flux. So due to the increase in the magnetic flux, this galvanometer is showing deflection in the sense the current is passing or current is induced in this coil, and the current is induced due to the EMF. And he also observed that this magnet that is moving away from the coil, when the magnet that is moving away from the coil, there will be a decrease in the magnetic flux. When there is a decrease in the magnetic flux, then also he observed that the galvanometer is showing the deflection. That is, induced EMF is produced. Even in that case also, current is induced in this coil. So from this he concluded that whether the magnet is moving towards or away from the coil, there is a change in the flux. Why? Because there is a change in the magnetic flux. So that change in the magnetic flux produces an induced EMF in the coil, and that further produces the current. So this EMF is called as induced electromotive force, and the phenomena is called as electromagnetic induction. Electromotive force. So what is this motional electromotive force? That is, what is the expression for induced EMF? So in this diagram, we can see that there is a straight conductor. This is a straight conductor that is moving in a uniform and time independent magnetic field. These crosses and all, we can see that those crosses are representing the magnetic field. So inside the magnetic field, a rectangular conductor PQRS is placed. You can see a rectangular conductor here. PQRS of length X and breadth L is placed in the magnetic field. Okay. So this end PQ is movable. It is not fixed in this rectangular conductor. So it can be moved in the magnetic field. So that is what we have taken. So here what I said, there is a rectangular conductor PQRS of length X and breadth L. So the area of this rectangular conductor, what I can say, L into X, because area of the rectangular is length into breadth, so X into L or L into X. And it is placed in the magnetic field. And what is the one more condition? That one end of this rectangular conductor is movable. That means this rectangular conductor PQ is moving in a time independent magnetic field. Okay. So this rod PQ is moved towards left with a constant velocity V. See, when this rod is moving towards left with a constant velocity, I can say for the next instant of time, this conductor will not be here. This one end, one side of this rectangular conductor will not be here. It will come to this position. So we can say that when this conductor is moving towards the left, there will be decrease in the length. So this X will change. Because say it is not at fixed position, it is moving towards this. So in the next instant of time, it may come to this position. So now the X is not equals to this value. Now X value will be changing. So there is a change in the X in the sense there will be a change in the area. When there is a change in the area, I can say there is a change in the flux. Why we can say there is a change in the flux? Because we have already discussed here. The change in the flux is depending on B, A and theta. It is also depending on A. So here that is what you can see. There is a change in the area. So when there is a change in the area, the flux linked with the circuit will change. And according to Faraday's law, when there is a change in the flux, EMF is generated. So what is that EMF that is generated? We are going to find out. So first, what is flux? When the rectangular conductor PQ, movable conductor is here, I can say the area is L into X. So what is flux? The maximum flux is B into A. So B into L X. So the flux is B L X. Okay, I told you already this SR and parallel to that SR is PQ. So both are equals to L. And here you can say PS and that is equals to RQ. Both are equals to X. So area of that rectangle PQRS is L into X and it is placed in the magnetic field. So the magnetic flux cutting across this area LX is BLX. Now this PQ is moving with a velocity v. So there is a change in the area. This change in the area produces the change in the flux because area is changing. So there will be a change in the flux. And according to Faraday's law, when there is a change in the flux, an EMF is induced. And what is Faraday's second law? E equals to minus d phi by dt. Here flux is changing. Okay. So EMF is generated. According to Faraday's law, E equals to minus d phi by dt. What is phi here? BLX. That you substitute in this equation. So if I substitute this equation here, what I will get? E equals to minus d by dt of BLX. Okay. So if you observe, this magnetic field induction is constant. Length is not changing. So that is also constant. So I cannot differentiate that with respect to time. So those two are constants with respect to time. So what is changing with respect to time? This x is changing because this one end PQ, we are moving in this direction towards left with a velocity v. So there is a change in the x value. So I can differentiate only that x. So minus BL, we get dx by dt. dx by dt is what? The rate of change of displacement. We know the rate of change of displacement is velocity. So this is v. We get E equals to minus BLV. So the expression for motional EMF is E equals to minus BLV. Here I did not write negative sign because we know negative sign indicates that the direction of EMF. According to Lenz's law, the direction of EMF is what? It opposes the original cause that produces it. Here actually E is developed due to motion of this PQ. So this EMF will develop and it opposes this motion of PQ. Okay. As it indicates only direction, the magnitude of EMF is BLV.